So far in our discussion of polymorphism, we've been focusing on lists in Coq. But of course, polymorphism makes sense with other kinds of data structures as well. Let's talk about pairs and options. So if we wanted polymorphic pairs in Coq, we could code those up in a similar way that we defined lists. So here's a type, we'll call it prod. We're thinking of this as product, as in Cartesian product. So we've got two types that it's parameterized, capital X and capital Y. You give prod those two types, and it gives you back a new type. So prod is another kind of type level function. With lists, we saw such a type level function that took in one argument. This one happens to take in two arguments. Now, the product type is only going to have a single constructor, which allows us to construct a pair of values. So the pair contains a value little x of type capital X and a value little y of type capital Y. So this is sort of the Cartesian product of the types capital X and capital Y. We'll use some of the same tricks we used with lists in order to make the syntax for this more pleasant. First off, we'll make the type arguments to pair be implicit so that we don't actually have to write two type arguments every time after a pair. And of course, the usual notation for pairs in math or other functional languages is going to be with round parentheses rather than having to write PAIR in front of each of them. So we'll use a syntactic notation for that. X comma Y in round parentheses is going to mean the same thing as pair applied as a prefix function to X and Y. We can even use that same idea of syntactic notations, not just for the values of pairs, but even the type of pairs. So we can define a notation X star Y as meaning prod applied to capital X and capital Y. Okay, so let's pay attention here to the difference between the values and the types. A pair of values is separated by a comma and has to have these round parentheses. But the type, which is the product of X and Y, capital X and capital Y, is just written with star here. And that refers to the prod type, whereas the parentheses and comma refer to the pair constructor. Okay, so X star Y here is intended to evoke the notion of like Cartesian product, which you might write with like an X in a math textbook. The little annotation on the end here, colon type scope, is giving Coq a hint as to where star means one thing versus another thing. Specifically, here star is supposed to mean the product type constructor, not the multiplication operator on natural numbers. Right, so Coq has a facility called type scopes that allow you to specify where certain symbols mean certain things, and they can be different in different scopes. We're not going to get too big into that right here, but that's what that was necessary for. Okay, so we can write functions on pairs now. Here's the classic first and second functions on pairs. So the first function is going to give us back the first component of a pair. So how do we write that? Well, first is parameterized on two types because our pair that we're passing in, we need to know the type of the first and the second component of it. We're going to take in a pair P, which is X star Y. So the first component has type X and the second component has type Y. And we're going to return, well, the first component of type X. How do we do that? With pattern matching, as usual for inductive types. So we'll match that pair against all the different forms that it could have according to the constructors defined in that inductive type. Now, what's different here compared to lists, of course, is that whereas lists had two constructors, nil and cons, prod has just a single constructor. So we only need to have, in this case, one branch in our pattern match. Maybe it makes it look a little diminutive, but that's okay. It's just fine. Match P against, well, what are the possible constructors? Only one, pair, and we have a syntax for that with round parentheses. So we can write X comma Y and return just X. Now, we could have written this otherwise. I could have written here PAIR X Y if I didn't want to use my syntactic notation, and I could have written prod XY here as well. That's totally fine. And maybe it's a little easier to see how that maps back onto our original definitions now. But I introduced that syntax because it's a little more pleasant. So instead of those, we can write what you might be more used to from other functional languages. Okay, so that returns the first component of a pair. We can do the same thing exactly, except for like that one character there to get the second component of compare. Just return y for second. Okay, so that shows us how to program with polymorphic pairs. Here's another function with polymorphic pairs. Go ahead and maybe take a look at this for a few seconds and see if you can figure out what this function does. I'll tell you in just a sec here. Okay, let's read this function together. What does combine do? Well, it takes in two types. It takes in a list, and that list has elements of type X. It takes in another list. That list has elements of type Y. And it gives us back a list of pairs. A list of pairs. Every element of that list is going to be a pair. And each component of that pair, well, the first one's going to be of type X. The second one is going to be of type Y. So it's like taking two lists and combining them in some way. What is the way? Well, let's read the body of the function to figure that out. We're going to simultaneously match Lx and Ly, the list of x's and the list of y's, against two things. In the first branch, we're going to see if the first list is empty, then just ignore whatever's left of the second list and return empty. The symmetric thing happens in the second branch. If the first list is empty, return empty. Or sorry, the second list is empty, then return empty. The more interesting thing happens when we've got other values. So if we've got x cons a tail of x's and y cons a tail of y's, then we're going to construct the pair x comma y and cons that onto the continued combination, the recursive call here, of tx and ty. So what does that function do? It actually combines two lists together as pairs. Sometimes people call this function zip. It's like zipping up two lists into one. And here's a simple example of that. Suppose you wanted to combine the list 1, 2 with the list 3, 4. That would get you back a list which has two elements in it. The first element is the pair of 1 and 3. That's the first of the elements of each of those lists. The second element of the output list would be the pair 2, 4, which comes from the two input lists. Okay, so that's how you can work with polymorphic pairs in Coq. We could also have polymorphic options. We've seen options before for natural numbers. We can generalize that and parameterize the option inductive type on a type capital X, as we've been doing before. So that would have two constructors, sum and none, and sum would carry a value X of type capital X. As usual, it's helpful to make the arguments to those implicit, and we could then program with those. I put this in a playground here so as not to interfere with other definitions from the standard library. We could write functions like giving us the nth component of a list, or the nth element of a list, and to do so in a way that doesn't require a default value, which is something that we had to do before when we weren't sure what to return because the list was too short. Right? We can't raise exceptions in Coq, remember. So instead of requiring a default value, another possibility is to return an option, and in fact return none if the client of this function has requested an element that does not exist in the list, or to return some v, where v is the element that is actually at position n. Okay, so the coding for this is really no different than how we would have done it before we had parametric polymorphism, but let's take a look through it once more. What do? We match the list L and see whether it's nil or cons. If it's nil, we return none, because no matter what n is, there's not enough elements in this list to get it. Like, even if we want the 0th element, remember these are 0-based, so right, the 0th element would be the first element in the list. There's nothing to return that's possible here, so we'll return none. Okay, but if there's at least one element in the list, then we have a hope, maybe, of being able to find the element that the client of the function is looking for. So now we'll take a look at n and see what n is. If it's 0, then we in fact do want the head element of the list. So at that point, we will return sum and that element a, which was at the head of the list. Otherwise, if n is the successor of some natural number n prime, well, then we don't want the head element of this list, and we know that we can continue looking for element n prime of the tail of the list, L prime. So we recurse. We call nth error on L prime and n prime. So we've kind of reduced each of them a little bit. We've reduced the natural number by 1, and we've reduced the list by removing its head element. And maybe that will eventually get us back an element, or maybe it won't. Maybe it'll return none, maybe it'll return some, but either way, that's what we're going to return as the result of that recursive call. So this is called nth error in a sense because we're implementing the notion of getting the nth element of the list, but we've got this error possibility indicated by none. Right? The error would be if you ask for the fifth element of a list, say, that only has 2 elements in it. Some other libraries might call this nth opt to indicate it returns an option. Either way, it's a good solution to requiring the client of the function to pass in a default value. So here is an example of using that. Suppose you wanted the 0th element of this list. That gets you back sum 4. Or suppose you wanted element 1 of this list. So they're 0 based, so that's the 0th element. That's element 1. So that's going to get us back sum 2. But if you ask for element 2 of a list that contains just true, that's going to get you back none because that's an error in that case. So that shows us how to use parametric polymorphism, not just with lists, but also with options and pairs. And you can do this for many other data types as well.